Hey guys, this is my first time doing it, so I'm taking you along the ride of doing some debugging in the context of brain-computer interfaces. Today, I think we have a very interesting problem. Just to put you a little bit in context, so I have a hardware developer that is currently developing the electronics of the Nucleus Hermes, a wireless EEG, in fact, multimodal data acquisition board. One of the system that is installed on the board is the ADS1299, which is a quite the gold standard in terms of EEG, EMG data acquisition. It's a ADC, analog digital converter. And currently we have a bug where the decoded data, so the board records the data, digitalizes the information, but the translation or the decoding of this information towards a let's say a floating point value, not necessarily a floating point, but more of the raw signal, currently doesn't work. I'm not sure at all what's going on. This is like I'm at the very beginning of looking into this. So the dev asked me to give him some help. What happens is that I actually worked with this system several years ago. So I probably built two or three boards with the ADS 1299. I'm a little bit rusty on hardware development, but I have some reference code that I have somewhere. I have the code that the developer wrote. I asked him to pick up some data so I can work with. And also the ADS 1299, I have like the data sheet to look into. So the idea is to take all of this all together and try to figure out, one, what's the issue? I mean, is it a software firmware issue? That is the software that runs on the microcontroller of the board. Is it something else? I mean, we already ran some tests. The hypothesis currently is that the data is accurately sampled. So that's the first thing that needs to be validated. So it seems like the data is accurately sampled. So now we'll look into like this decoding process. If we can bring the understanding a little bit further and see like, okay, is it where the problem is? And from there we'll conclude either try to fix or try to push further the problem. So I'm taking you along the ride of a debugging problem. So what I'll do now, I'll just start to assemble all the documents, all the elements I have to get started, and then I'll connect again. So it's gonna cut now, okay? I'll connect again once I have like the table set for the debugging process. Hey guys, so I'm back. I got several of the documents I was looking into assembling. So what I went to get the ADS 1299 data sheets. This one is freely available on the TI website. This is a document if you develop with this chip. I mean, there's two documents. There is the ADS 1299 EG front end documentation, which is super important, and then there is the data sheet itself. And this is what it looks like if you've done any type of electrical engineering development, you're familiar with this type of documentation. But what you'll find in there, besides all the performance charts and all, what you find inside schematics of the chip, you'll find the register map, okay, here with all the details for each register. This is super important. This is what tells you how to configure the chip. But generally, it's quite heavy to read everything. Towards the end, they generally provide some kind of like sample application, more straightforward application. So this is the starting sequence. This is super important. If you don't do this, the chip is not going to work. This should be your starting point. That is, when you start to develop with a chip like that, the first thing you should achieve is just to run through like basics examples, or at least basic applications such as what you have here, and then you customize based on your need. So this, I will be looking into this in the code to see if it's done properly. I suspect it is because the chip is recording at the moment. And then a few more. So how to configure. So this is super important when you start to build your circuit. The other one that I find that is, now we're not going to do hardware debugging. But if we were, we would be very much interested in looking in, I think it's 46. 46 here. So you see, so the now it might not be exactly this one, but you're looking for like some timing diagram here. It tells you the whole sequence of how the signal should proceed. This, if you work with the logic analyzer, this is what you can record from. You can sample from the board to ensure that everything works properly. Now, for now, in this specific in the current scenario, we take for granted that the hardware is working properly, and that the startup sequence is working properly. So we're only investigating the program itself, the firmware. If we find issues, if we don't find any issues with the firmware, then we might roll back and try to figure out like is this diagram respected, but for now we take for granted that only the firmware, and most likely is the conversion data conversion itself. So ADS data sheet, we have it. Reference code. So as I said, I already built a functional version of this of an interfaces to this chip. I have one in Python here that I wrote, you see, 2017, so several years ago. I'm a little bit rusty, but this is something I built back in the days. So this is one in Python where the conversion is done right here. So this, I'll be looking into this to see if the conversion is done properly. And I have one as well in C, roughly same year, and this one, like I said, I mean, the conversion, I don't think the conversion is done with this one. I think it's only does a sampling, but the startup sequence is programmed here. So anyway, the point being that I have two reference code that I wrote. Both of them, I know they work. Okay, so these two projects work properly. This one, by the way, was for the Raspberry Pi back in the days, but there was no way to actually get it to work straight with the Raspberry Pi due to operating system. Different discussion. Now, what I have in terms of information to get started with. So actually, I discussed with the dev, and I forgot, but what he told me basically is we ran some tests already. What he said is that, okay, look, the main issue, so we have a ground here. I asked him to record some ground, so a 0 volt. You see it's offsetted from 0 here. So this is curious here. But anyway, so we have a ground, then we have a 2 VDC, which also seems to be 2 VDC. So this one shouldn't be like in the negative range. So again, but what we're looking is not only like the value, the absolute value, but also the shape. And what we find here is both are DC components. After the starting phase here, both are DC components, and they seem to be stable. And then we failed to find here, it's a 0.2 volts peak-to-peak sinus wave, and the frequency is 50 hertz. Okay, and this is well within the bandwidth, admissible bandwidth of what we're trying to do. We're sampling at 250 hertz, which means that we should be able to sample very correctly anything that is between 0 and 125 hertz, give or take. Okay, that's the Nyquist frequency. Okay, one thing that just to know, the Nyquist frequency. But the point being here that 50 hertz is well within our bandwidth, so we shouldn't meet issues with sampling 0.2 volts peak to peak. Now we see all these oscillations. I mean, it does show that it's not like a straight line. and this is the starting point of what we have. So this was raw data. I think this was from an earlier email. This one was less defined anyway. So that's another thing. And I think this one here. So what's this one? So now we have two VDC. Oh, you see, that's a different recording. I have to see why this one has different values than the other one. But we have, you see here, 2 VDC, 0, and 0, 2 peak to peak. So it seems like something's working, not too, so there's an offset here. There's an offset here. This one should be on 2 volts, technically. Okay, and we see that the 0.2 volt peak to peak is in between. So now, what's happening? That's what we'll need to figure it out. But we have like these pieces of information to just say, hey, this is a problem we need to be fixing today. What I have beyond that, I've just noticed I don't have the code sample. So I will have to, I'm missing the code sample. Code to debug. So the reference code, we have it. Code to debug, I don't have it. I'll look in my email. It shouldn't be too far. And we do have data sample. Just show you here. So I will have to look into it. This one seems to be the most complete. I have 8-bit. Okay, so the ADS1299 outputs on 24 bits, signals that are on 24 bits, integers. So we break it down in 8 bits. And then here's the assembly in 24 bits. So there could be actually an issue with the way that these elements are assembled. So you see, so channel 1 and channel 2. So I would expect these 3 to match onto this number and these 3 to match onto this number. So this will have to look into it, confirm that it works. And then there's a 2 complements conversion, 24 bits. So the 2 complements is the encoding, is a sign encoding of integers. The basics of 2 complements is simple. Is first you have like all the binary code. So the binary code, if I go with, let's say I go with 8 bits here. So this is obviously 0. This is 1. This would be 2. Okay, so this works fine. So this is the binary code. Okay, so this works. Now, when it comes to signed integers, which signed means that they can encode negative values. Now, there's the 2 complements that comes into play. The 2 complements, the logic here is that I always remember one specific number is this one. This is -1. Okay, and the way you convert it, the way you find it's -1 is, so this is a negative number. This is the bit sign. So if there's a 1 here, it means it's negative. Okay, and everything else encodes the number. So the way you find the value of a negative number is first you invert all the bits, and then you do +1. Okay, and now I found the positive value associated with this negative number. So I always remember the -1, and then I can just work back the problem to figure out like how 2's complements works. So basically the principle is this is how negative numbers are encoded as integers. And now this is an 8-bit representation here. We're actually working with 24 bits. Which is a little bit surprising because on computers you generally work with 8, 16, or 32 bits, or even 64. Now we happens to be working with 24, so it would mean that this is times 3. Okay, so this is the number of bits we're working with. Okay, and so the conversion here is to go to see how do we go. So if we backtrack to where we were, so we'll check. Okay, are these bits here? Okay, this is a binary representation. This is a decimal representation. And there's also the hexadecimal representation, which is super convenient. And that's the one I generally prefer. So hexadecimal, what is nice is that you can actually encode quadruples of bits into a hexadecimal representation. So this one would be 0, 1, 0, 1, 0, 1. And you see this is an hexadecimal representation of the bit sequence here. Hexadecimal is not convenient to do math, but it's very convenient to understand your bits in a more compact fashion. So so I'm surprised that here we have integers, but I'll show you the trick here, what we use for, if you want to go a little bit faster, you go with your calculator, programmer calculator, and then you can do your conversion. Invalid, probably because binary here. Let's see what happens. You see, so this is the hexa representation. Now you have to figure, it drops the 0 here, but besides that we have it. Then there's a decimal representation and binary, obviously. So now let's say I have like 177 here. So this is a decimal one, and I expect to find that the binary representation is corresponding binary representation is this one. Now, if we look for these numbers, these I suspect will be negative numbers because they have like big numbers. This one's the biggest. So this, you see all the ones here. So this is a negative, likely to be a negative number. 1, 2, 3, 4, 5, 6. So that's a 24 bits representation. You see, this is most likely a negative number. So you see, this is all the stuff I'm going to be working with for the next half an hour. Just put the ideas all together. Let me just summarize here. To move forward from this problem, you need to understand 2's complement. Okay, that's how signed representation for integers, bit X and decimal representation. We need to understand them and to be able to work between them. So you have the theoretical understanding, and then you have like the calculator here, the programmer calculator, that just makes the whole process much faster. You can also program it or display it in Python or whatever. And now the plan for now is I need to find, I know I have it, I need to find the code to debug. I don't have it on hand right now, but it's in my mailbox, so I'll figure this out. I'll do a review of, I'll start with a review of the code, just a quick comparison with reference code, just to see if they line up. I might have also to add some comments to the code to debug, just to figure out like how get into the problem of what has been programmed and how it works. And sometimes, I mean, I don't think I will, but I could land on some issues right there. Then I'll work on the conversion problem. Okay, I'll probably what I'll do is I'll program a sample code that does the conversion. I'll build a reference test with the proper a reference test with values with known outputs, and then I'll feed recorded values and see if the output match the documentation received. So this I should be able, by doing this, I should be able to tell if the conversion implemented by the developer matches what I would build as a conversion code. If it doesn't work, reference test from reference code. So I'll just take it from reference code. So the goal here is to build a workflow where I can convert some values that I know will work from a reference code that I know works, and then feed the same values that were recorded by the current PCB and see if I fall onto the same value. If I don't, it means that the problem is in the conversion from the code of development. If it does match, then we have like I have to work out some new hypothesis. But for now, that's the current goal post. Okay, so once I get there, I'm back on the video and see what's up. Hey guys, we're back. So we're probably an hour into it now. So I haven't found any bugs right now, or at least I'm as confused as the dev, as it's still not working. I did make some progress though. So let's see what's happening. So first of all, in the code, I've noticed, and in the files as well, I've noticed that there were 9 data streams. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I wasn't sure there's 8 channels, so why 9? But I look into the data sheets and I found that the first byte here is actually the status register. You see now the value is changing here. That's curious here, because I would expect this to be a constant value. I have to look into this. Why? What is changing? Why it's changing? Could actually be you see, it's repeating, so the same values are coming up. Okay, we'll look into it. So I'll just add this to the hypothesis, and why is status register changing? Could be normal. The way I see things is that sometimes little details will point you in the right direction for the bigger issue at hand. So it's super important. So anytime you see something, even if it's not directly related to your problem, anything that you see, say, oh, that's curious, add it to the list. You'll get to it at some point when it makes sense. I mean, I'm not saying this is a priority to look into the status, but this is now on my list. Now let's focus. So yeah, status register plus 8 data channels. So this makes sense. So we have so this accounts for all the data that we get. I look quickly at the code. Makes sense. The code seems to be, at least it's well organized. It's well programmed. This gives you an indication when the code is disorganized and chaotic. It tells you that the person who programmed it didn't have clear mind, but now the code is in order. So but that's the next step. But at least the first overview of the code led me to think that the code was probably okay without looking into the details. I did find one thing, an hypothesis. So I was looking at my sample code that I have, and I've noticed that it actually unpack in little endian. So little and big endian is kind of like a confusing notion in computers. It depends on how the bytes are organized. Generally, if you stick to one machine, let's say 64 bits Intel and all over the place, you shouldn't run into major issues. But when you start to work with microcontrollers and the like, sometimes you run into situations where little and big endians can matter. The bit ordering might be different from one system to another. I look into it in the sense that I say, okay, let's take this opportunity to just try to unpack and do the conversion, and while testing for hypothesis in terms of little and big endian. I didn't find anything there, so I don't always code in Notepad++. By the way, I'm just running quick stuff, but no. Once I run through the conversion, everything looks fine. I did get one indication that the conversion was happening properly, and it is that here. So first, okay, this one I'll talk about it. So I was able to decode the signal from the raw bits, and let me just show you what comes out of it. So what we get with the full conversion, we get a 0.1 minus 0.1 to plus 0.1 signal here in volts. So it's a 0.2 peak to peak centered on 0. And the details, what the dev told me is that this channel was supposed to contain a 0 centered 2 volt peak to peak signal. So what happens here is that it seems that I'm decoding some things that is 10 times lower in amplitude than what is expected. Now, a factor of 10 could be because of the conversion. There's actually a constant value that is used to convert the bits into volts. So maybe there's a 0 here. I will have to check into this. Let me just take note of it. Conversion 10x too small. Maybe this is it. Maybe the conversion factor is too small. But the point being that the fact that we get this peak-to-peak value is kind of like a weird coincidence when you think that it's very close to what was expected. So this right now leads me to the hypothesis that we are decoding properly. But there's still something. It still doesn't work. We should see here a sinus, 50 hertz. I did the FFT of the signal to see the frequency content, and you see we have nothing here at 50 hertz. It's kind of like it's white noise at this point. I mean, you see that the frequency power is equal everywhere. There's a little bit like, because here it's not, the average is not perfect, so this is the DC component. We see that the signal is just a little bit offsetted from a 0 average, because this happens when you have a very short sampling. So right now it seems like the signal is definitely not there. I do think that we are decoding properly. So now what's happening? I still don't know. Okay. I was able, I did a second test where I just went into replicating the graphs that were sent to me for signals. I just show you again. Let me just fix. Like I said, this is not production code. This is just like a quick setup to see what's happening. So this works. Don't need this. So let me just print here. So this is exactly what was sent to me. That is, if I open this one, I think raw converted. Yeah. So okay. So this one here, you see, and the one I obtained. So it's the same file. Obviously. So it's not a big reveal here. What I'm curious about, it seems like the values are the same. I haven't matched the values, but I'm really puzzled as to why. Oh, what's the value here? Am I still getting this 0.1 here? See, now it goes to 8. Okay. What I'm really puzzled about here is why we have this offset here from 0. This signal here, channel 2, which is orange, should be. And why is this one negative? You see, there's still something here in the decoding, that is, these values should be straight on their expected value. They shouldn't be like a little bit aside from it. So one of these two should be on 0, and one of these two should be straight on the 2 volt. There's also the questioning about the 2 volt peak to peak, but one thing at a time. So where I am now in terms of the plan. Why is the status register changing? This could reveal some issues in the way the bits are read. So this could explain something. There's a conversion factor that is 10x too small according to what is expected. So I'll confirm this value again just to make sure. So now I'm really into like what is the register configuration. So it's really about like now I'm reviewing the code. What is the setting of the ADS? Try to figure out like, is there an issue in the configuration? And this is the next thing I can look into it. I don't have the board with me right now, so I'm really forced to stick to the code. But I'm narrowing on the idea that maybe I will need to look into the hardware itself. But if this happens, it's going to be a different. It's going to involve a different approach. Anyway, so it's just to keep you guys up to date. I keep on going to try to figure out what's going on. Hey guys, so this is the last entry for today. I did find something as it turns out. So I look at the firmware. So first, the firmware that was written for to operate the ADS1299. Overall, the software, the firmware seems to be okay, but I've noticed that the settings for set acquisition, so the settings here for the registers, config 1, 2, and 3, as well as the set of registers that that configures the channels. There were a few differences. So in config 1, and just see here, oh, I don't want to lose this page. Which page is that? We'll get back to this one, figure 42. Okay. So config 1, here, let's go see. This is the one that has the output data rate, the sampling rate basically, and currently it's set at give me a sec. It's set at 9494. So 9 is 1001. Okay, so daisy chain mode. This I'm not sure, but it's the same value in my own code. So this could actually be okay. No output, that's okay. So this is when you assemble multiple ADS1299. This is what you get, like the daisy mode, when you want to have like 8, 16, 24, 32 channels. You daisy chain the chips, and you need to propagate the clock this way. But the one that is interesting, so we have 94, and 4 is equal to 100. So we have a sampling rate of 1 kilo sample per second. My requirements are for 250 sample per second. But I asked the developer to run the test with a higher sampling rate. That's probably why he's running at 1 kilo sample per second. Now it just hit me. So that's probably what he wanted to use. It's 4 times higher than the sampling rate that the requirements of for the board, but it's probably to test it under pressure, high pressure. So that's okay, but this anyway, in any case, this wouldn't have explained, because even if you oversample a signal, you should still find the sinus, no, just oversample. No, so that shouldn't have, this shouldn't be an issue, but okay, the gain configuration was set to 1, and I expect a gain configuration set to 12. This could explain the difference of, I found 0.1 peak to peak, where I was expecting to find 1 volt peak to peak. So this could actually explain that, because from 1 to 12, there's roughly a factor 10. So this, I'll flag it to the dev to see what he has to say about this. But even then, I mean, that still doesn't explain the fact that we can't find the signals we're looking for, as well as the offsets that we find in these metrics. But I did find something else, and I think this is where, so at some point, I said, this is curious. I was looking at these numbers here, and I was like, this is curious, because this is the status bytes. So there's 3 bytes, 24 bits. And let's go back to figure 42. Figure 42. Yes. And what we find here is that the content of in the output, so 24 status bits, plus 24 times 8 channels. So that's the total here. And the status bits is 1100. Then those are the registers, the lead off for positive and negative electrodes, as well as the GPIO registers, the bits for the GPIOs. What we see here is that we should find 1100 all the time here. We are not finding this. In fact, what we're finding is even more curious than that. So I was looking at the value and something hit my eye. You see 188 here, 188, 188, 188. Now, we probably drop a few sample here, but here, look, here it's 13 sample of difference here, 13 sample again. Now here we probably dropped a few because this should be the 40th line, okay? Same thing, look, the value that follows, 240. 240 follows the same pattern. Let's go back, let's go down a little bit. You see 240, 188, 188, 241. You see here? So it's the same, and now here what we're at, we're at 11, 7, that's 13. That's 11 now. So, okay, the point here, there seems to be some kind of regular upcoming of these values. This, you see, I mean, if the GPIOs are likely to be grounded, so we should find zeros there. The lead off, lead on, maybe there's some detector that kicks in that change the values, but we wouldn't expect anything to be as regular as what we find here or as periodic. We should find something that is either a fixed value that repeats or a random part. Okay, fixed values plus a random element. Now this is the first thing that caught my eye. Then I went into the documentation and I found here this should always be there. The 1100 should always be there. Okay, and that's 3 bytes, by the way. And then I started converting the integers that we find here into their binary value. First, they all fit on 2 bytes instead of 3. In fact, they should be 24 bytes. Okay. Oh yeah, that's even worse than that. Okay, I have to look a little bit more into it. But you see, this is only 1 byte. 1 byte goes from 0 to 255. So there's something off here in the way this is displayed. Let me just check. Let's just check real quick. Okay, there's something odd here. I don't think I have the code to print the data. Let's just see, maybe there's something here. Print data, okay, RX0. Here there's a conversion of 2's complement. Okay, I have to see with the dev what is supposed to show up here. You see the same value here, starting in it, because this is okay. So I have to see with the dev what these values are and why we're not finding the pattern that we expect to find here, and the fact that they rotate like that. I say rotate, I mean I kind of like concluded that there was some kind of like elements of rotation here because they repeat. It could be a bit shift. You see like the 4 bits here, the 4 bits here. Maybe there's something here. Anyway, the point is, I'll talk with the dev. I do think that this is not normal, and this could be the first thing to look into towards debugging the data acquisition, because besides that, I didn't find anything that was suggesting that the chip is not working itself or that is misconfigured to a point where it doesn't work. So what are the steps now? First, I'll talk with the dev. Okay, try to see, find an explanation for what we're seeing now. Okay, it might seem like the status bits, we don't use them in our application, but no, from experience, when you find something that doesn't work like that, it could simply be the sign, the symptom of the problem we're actually looking for. So this is something I want to look into and explain. So that's the first step. The second step, what I would really like to do is actually to connect and sample using a logic analyzer. Okay, this is the last step. This is the bazooka in the problem. So you connect and you see the actual pins, the actual trace. You see each bit, the 1 and 0s that you see here, and you can really compare what goes on the line, what goes on the line, and what goes into your print and your registers. And so this, I would really like to, this is how you generally solve these kind of problems when you reach this level of investigation. So this is the end goal if we don't find it before. But the thing we can try in before that is the test mode. So the ADS1299 has a test mode which outputs a, we can find it here. Just let's just find, so there's a test mode where you can get the channels. You connect them first to conjunction with bias, test signal. You connect them to the test signal. And what you find in regard to the test signal, okay, you have the configuration here. What you find with the test signal is it's a square wave. Okay, signal frequency test, I don't know, probably bias test. Okay, anyway, I'm not gonna bore you. Register, okay, here it is. So config 2, the test, so it generates a square wave where you can control the frequency and the amplitude. I mean, basically the idea is just to set it to some value. And the test signal doesn't depend on the input. So it really makes it possible to validate the chip without looking at the input pins. So you can ensure that from the SoC, the chip, all the way to your software, you have a known signal with known properties in terms of frequency, amplitude, so you can validate the whole sequence of events from there. The dev did try the test signal. I just don't know if he spent all the time required to ensure that your square wave is always the same length up and down. The frequency matches what your expectations. The amplitude matches your expectation. And this test signal can be used to, will be used to, and I think through this, we should be able to tell if we're reading the data properly or not, because I suspect that we are not reading the data properly. That's what I think the issue is. I did notice one thing in the code that could maybe explain that. So when we're reading multiple, read, register, we should try also to read register. This should help. Where did I find the reading? Here, I believe, read data. So here, I don't know how this behaves here, but there's a for loop here that repeats the number of read bit that we should look at, that should be processed. This function here should, I believe, instead of being in a for loop, it should have as input parameters the number of value that you want to read, and it should buffer the whole thing all at once. The issue that you have with this is, I still don't know what this one does here, but this could induce a little bit of delay between your read and just enough to get you off track in terms of reading all your bits. And this could maybe explain why the reading doesn't work properly. Now, This is the last entry for today. There's been some progress. I mean, you don't fix every bugs in a single day. I think it's interesting to share what. So this represents roughly 2 hours of work to give you an idea of investigation. It provides an insight into what it is to be a developer, to review some code, review some problems, and try to figure out what the situation is. I think you don't always end up finding the bug, but the idea is always to build new hypotheses about what could be wrong and then validate one after the other, do all your checks, and at some point you end up like finding which one is the actual issue. So that's how it works. That's the debugging process. If I had all the stuff, the hardware with me and everything, I would probably proceed today. Now, because the dev has the hardware, the prototype, and we're working asynchronously, so I'll send him the information I got, try to schedule some tests with him. If really can't proceed forward, I might ask him to hand me the prototype so that I can conduct the test. But he's experienced, so I think he's going to be able to, with this little bit of extra information, I think he's going to be able to figure it out. But so I'll keep you posted. I didn't have big plans for this video. I mean, I don't know. I'm just trying to put some content on the YouTube channel, and I thought that sharing with you the day-to-day of a developer. I'm wearing my developer hat right now. Could be interesting. So anyway. Hope you liked it, and I'll let you know. Anyway, in every case, I'll let you know once we find the bug. I'll let you know what was the issue behind it. Okay, have a good one. Hey guys, last entry. I think we figured it out. So I just had a chat with the dev. We look into it. We found something. So here I didn't know what this was for, and if you look at so here is the read data of the ADS, and this should fit into the timing diagram, which we find here. You see RDDAC should be sent once, and then every time this pin here, the DRDY, is the one that that signals that the sample is ready. When this one goes down, everything else kicks in. Okay, so this one should be sent once, and you see when you write, you'll actually trigger the clock here. Okay, now look at what happens here. So when the RDY goes down, you should have an interrupt. You should have something that monitors it, either an interrupt, or if your MCU can just like poll it. And when this one goes down, then you should start the clock and read status register and all the data here. Now, what happens? This is called, indeed, you see GPIO read pin. When the RDY goes not, then you start to read data. When you read data, it will count 3 plus number of channel times 3. That's the number of bits we want to be reading. But then here, it starts to transmit RDDAC again. And the issue here is that by transmitting, it triggers the clock here. And basically what we lose then is, so we were looking at, so this is, what is sent here is 1 byte. Okay, so here we have 1 byte. And what we found is that if you send 1 byte, it means that you're skipping 8 bits out of the status signal that we saw here. Okay, the first one is the status bit, status 3 bytes. Okay, and what happens is that because it's sending the attack first, sorry about that, data in, data out, where is it? Here, we end up missing these 4 bits plus the first 4 of this register. So we miss all these bits. Now this is set to all zeros, this is set to all zeros, and this is also set to all zeros. So it means that out of the 24 bits, we miss the only ones that were coming, and we're left with 16 zeros before the data comes up. And if we look here, another curiosity was that here we only have integers that are between 0 and 255. And 0 to 255 is 1 byte. Okay? This, we know this when you look at, so let's say we just go in binary mode, 1, 1, 1, you see it, 1, 1, 1, 1, you see 255. So it means that here there's 24 bits, but all the values are within the last 8 bits. So it means that it's preceded by 16 zeros. This is why we don't see any bigger number here, is that before here, not shown, are 16 zeros. The same 16 zeros that we're missing right here. Okay, so the conclusion to this is that we found that this is not the status byte, but it's rather the beginning of the actual data acquisition. So everything is shifted by 8 bits because the code sends the transmit first. So listen, not sure 100% that this is the issue, but it definitely looks like this is the problem, the bug we were looking for. So this will go away, this will stay the same, and now we should have the status bit should be fine. So the status bit should be the value that will be as part of the status bit will be 1100 and then 0000000. Am I missing any? Okay, now and 0000000. And we should find that the first number, if I'm not mistaken here, 1, 2, okay, so that's 24 bits, 1, 1. We should find, now it says a decimal of 12 million, but that's not true because we're actually in 2's complement. Now I'm not sure it can compute here the 2's complement, so we'll leave it at that. But the point is that we should find a negative number, and it should be it's not going to be this number, but it's definitely, this should be the status byte, and this is not what we have. So it seems to make a lot of sense. Further, we even noticed something else. You see how cyclic here, and not only cyclic, but look, it's symmetrical. 188, 242, 240, 189, 190. I suspect that what we're saying is that channel 1 was actually having a sinus wave. Okay, so, and I suspect that what we're seeing here is a sinus wave. Now, we're speculating, there's not much value into like actually investigating if this is really the sinus wave. So we'll leave it at that. We'll wait for the bug to be fixed, and then we'll see if we have good data now. So hopefully it is, finger crossed. Otherwise, I hope you enjoy. I mean, this is, like I said, this video is really like a debugging session. I don't know if this kind of content is of any interest, but I just thought that it was a nice look into the work of hardware and software developer, and I hope you enjoyed. Okay, have a good one. Bye bye.